I'm going to ask one other favor. I just remembered, normally what I'll do is record our sessions so that if you want to, you can go back and look at it at a later time. I just realized that I hadn't done that. So somewhere along the line, if somebody remembers at the start of class, can somebody say, did you remember to hit record? Okay, so like charges repel, unlike charges attract. Going back to our battery for a minute. We had this plate, had all of the atoms had the same number of protons, same number of electrons. The chemical reaction caused this electron to get yanked away from the atom in the plate and go into solution. Same thing with this electron, got yanked away from its atom, went into solution. So now, if I just looked at the plate itself and counted up how many total protons there were and how many total electrons there were, not counting stuff that's in solution, would they be equal anymore? What'd you say, Tony? I saw you shake your head. I have you up on the screen over here. So who's got it? Do we have it or not? Are they equal or not? This is the part where somebody replies.
They're not equal.
They're not equal. Okay. What have we got more of in the plate?
Protons.
More protons.
We have more protons than we do electrons. That means that this plate has more positive charges, more protons, positive, than it does electrons. That means that this turns out to have a net positive on it. Okay. At the same time, sitting over here, we have a bunch of electrons, and all of these electrons in solution, and this chemical reaction has taken this electron and moved it into the plate, and has taken this electron and moved it into the plate. So what can you say about this plate?
It's negatively charged.
It's going to be negatively charged. So this is going to be a net negative. And if we think about a battery, batteries are always labeled with positives and negatives, plus and minus. The way that happens is there's a chemical reaction that takes place that moves electrons out of one plate into the chemical medium. For a car battery, that would be usually sulfuric acid. And then the other chemical reaction pulls electrons out and brings them into. Now, what did I say about all atoms in their natural state want to be what?
Electrically neutral.
They all want to be electrically neutral. So that means that I got electrons over here saying, I don't want to be here. I want to be back over here. But I got no way to get there. And I got this guy saying, I really need a couple of electrons because I'm missing a couple. So now what we do is, if I now took and connected this is the symbol for a light bulb. If I now took and connected a light bulb across them, now I've got a path for the electrons to move through what we call the circuit back to the post or this plate that we want them to go to. Okay, so now the electron that was over here that didn't want to be has a way to get back to this plate, which is looking for an electron. And this electron, which didn't really want to be here, has a path to get back to the plate where it wants to be. But what's happening? While all of this is happening, we still have the chemical reaction pulling electrons out, and this chemical reaction shoving electrons in. But each time electrons get pulled out of here and shoved into here, the chemical weaken. And what's going to happen at some point?
Gonna die.
Huh? Say again?
Like the battery's gonna die, I guess.
The battery's going to die because the chemical reaction isn't strong enough to force the electrons out of one plate and into the other plate. And that's how we end up with a dead battery. Now, depending on the battery type, what we can do is, if you have a car battery, you can rejuvenate or restore that chemical balance and get it back so that it can start all over again. If you have a carbon zinc battery, the old style flashlight batteries, once it's dead, it's dead. There's no way of recharging it. Okay, so there's a couple of important takeaways here. The first is that it's a chemical reaction that causes the electrons to leave one plate and go into solution or into the chemical, in this case it's a solution, and causes electrons to go into the other plate. That's what gives us our net positive terminal and our net negative terminal. And it'll sit there, and if we create an electrical circuit that provides a path for the electrons to move, okay, then electrons can move from where there's an excess of electrons, the net negative terminal, go back to the post where there's a deficiency of electrons, the net positive post. And that reaction keeps that going. Everybody with me so far? And again,
Yeah.
if you worked for Duracell, they would look at this and go, really? There's a lot more to it than that. And that's absolutely true. But for what we're doing, this is fine. The second takeaway is, what moved around in the circuit? The net positives, the electrons or the protons?
Electrons.
The electrons moved. Okay, the electrons moved. It's the electrons that move through the circuit. Okay, we're going to be dealing with, there's two ways of looking at electrical circuits. What's called electron flow and what's called conventional current flow. Most electrical engineering courses, most electrical engineering technology courses use conventional current flow, not electron flow. A lot of military training and some trade schools will use electron flow. It makes sense to use electron flow, but it's all Ben Franklin's fault. He said it was the net positives that charged, that moved, and it became the standard. And we'll talk about how we can envision that the net positive moves, but not the positive charge itself, not the proton, all right? But let's do this. Let's take about a 10-minute break. By now you've been sitting undoubtedly too long. Take a minute, stretch. Let's be back. It's 2:24 now. Let's go 25 to 3. We'll take.
Sorry, Professor. I have a class at 2:30. How long is this class?
Oh, I'm sorry.
Yeah.
Oh, yeah. Okay. Yeah, that's it. I'm sorry.
Meeting Mr. Atwood at 2:30.
Yeah, me too.
Oh, okay.
And
Well, if you're seeing Atwood, then you can ask him about the what's going on Thursday. I won't have him send an email. Just ask him what's going on Thursday. All right. I'm sorry. I didn't realize we were running late. We'll see you on Thursday, 1 o'clock.